Let's briefly review some of the rules for basic probability that everybody needs to know to move forward in basic statistics. Okay, so a probability, the probability of A, any probability is really the number of occurrences of something over the total number of possibilities for that. We often use the letter S for the number of occurrences. S usually means success versus failure, but it's up to you what you want that to mean. But it's the number of occurrences S over the total number of possibilities N. So it's always that kind of fraction, which means the probability of something will always be between 0 and 1 inclusive. So if something can't happen, the probability is 1. If something has to happen every time, the total number of occurrences will equal the total number of possibilities, and the ratio will be 1. So whenever you're calculating a probability, make sure you end up with something in between those two values. You wouldn't believe how often I see on quizzes and tests and homework that people calculate probabilities that end up either being negative or greater than 1. So the very first thing you should spot when you're working on a probability is, do you have a number between 0 and 1? If you don't, you probably forgot to do something in your arithmetic somewhere along the line. Okay, so if the probability of something happening is between 0 and 1, the probability of something happening overall is 1. So if you have successes and failures, no matter what the percentage is, they're going to sum up to 1. So one of the rules of probability is that if you know all the events that can happen, the sum of the probabilities of all those events adds up to 1. Sometimes in statistics we'll see that our events don't add up to 1. That doesn't break this rule. It usually means that it's one way we discover that there are events and opportunities for things to happen that we haven't considered. But generally, if you have an exhaustive list of all your events, the probability that one of those events will happen must add up to 1. Another way to put that is that there's a relationship between the probability of something happening and the probability of something not happening. So the probability of something not happening is equal to 1 minus the probability of it happening. Or conversely, the probability of it happening is equal to 1 minus the probability of it not happening. That's a very important formula when you're calculating a lot of probabilities, because there's some open-ended problems where it's not possible to calculate the probability of something happening. All you can do is calculate the probability of it not happening and then subtract that from 1. So that last equation there is more important than you think in solving a lot of engineering challenges. When you're combining probability from multiple events, one of the ways we do that is we use the OR. So the probability of A or B or both happening when two events are not mutually exclusive, meaning they could both happen. The probability of someone being, say, male or female, and the probability of them being an adult or a child, those probabilities will overlap because they're not mutually exclusive. The probability of being male or the probability of being female would certainly be mutually exclusive, but many, many events are not mutually exclusive. So the probability when you're looking at A or B or both on non-mutually exclusive events is the probability of A plus the probability of B minus the probability that they could both happen. And the reason we subtract that probability of both is we don't want to double count those items that overlap in the probability of A and B. So assuming you've got an event that's both A and B, it's considered in the probability of A and the probability of B, and therefore it's been double counted, which is why we subtract the probability of doing both. If we know that A and B are mutually exclusive events, meaning they can't both happen, then this is a simpler equation, the probability of A plus the probability of B. But it's really the same equation, because if they're mutually exclusive, the probability of both is 0, so it's probability of A plus the probability of B minus 0 in the first equation. So these aren't really two different equations, but they're two different ways we talk about probability over time. Sometimes we're trying to take the probability of A and B happening. If we got a dependent event, that the second event is actually dependent upon the first. So if I catch a flight to Chicago and then have to get from Chicago to Los Angeles, the probability of getting to Los Angeles is not only dependent upon being on time in Chicago, but I've got to catch the flight. So I have to have gotten to Chicago before I can really calculate the probability of getting to Los Angeles. So that's an example of a dependent event. So when I have a dependent event, I want to know the probability of A and B happening. It's the probability of A times the probability of B given that A has already happened. That's what that bar means, the probability of B given that A has already happened. So I'm multiplying the probabilities because they both have to happen. And the probability of B is dependent upon the event A having already happened. If I know two events are not dependent on each other, they are completely independent, then I simply take the product of the probabilities. So the probability of A and B happening is equal to the probability of A times the probability of B. Again, those are really the same equation because if they're independent, the probability of B given that A happens in the first equation is equal to the probability of B because A being mutually independent events, A doesn't impact the probability of B. So really, again, these two equations are actually the same, but we tend to talk about them in two different ways. Let's look at an example from engineering of some of that information applied to things we actually worry about as engineers. One area is in the area of system reliability, because reliability, when you learn that in quality engineering or reliability engineering, you're going to learn that reliability is always a probability. So just like any other probability, it's the ratio of successes to the total. So again, all the rules of probability apply. It has to be between 0 and 1, and all the additive and multiplicative rules I just talked about would apply to reliability measures as we go through. So I'm putting together a system where a series of things have to happen. So step 1, step 2, step 3, right on down the line. If everything has to happen, if any one of them fails, I'm in trouble. That's an example of a process that executes in series. So the reliability of the entire system is dependent upon A and B and C and D right on out to N having happened. And we saw in our equations that when we have an AND, like in series, you multiply together the reliability. So the reliability of this process is the prod sum of all the reliabilities in it. So I have two different steps that are 90% reliable and put them together. The combined system is only 81% reliable. If I take 5 steps, each of which has 90% reliability, the overall system only has about a 45% reliability. So when I'm working in series, I'm multiplying values. And since every value is a fraction, probabilities and reliabilities in series always go down. The more steps I have, the lower the reliability, which is why a 90% reliability, even a 99% reliability, often isn't good enough because I put together components in a series. And the reliability of the overall system falls quickly, even though each of the individual components might be considered very, very reliable. So reliability in series is an example of AND logic, and we multiply the reliabilities and probabilities. When I'm dealing with things in parallel, I'm dealing with OR logic. Presumably, if I have these 1, 2, 3, 4, 5 to n steps, any one of them working will keep the process moving. So this is one of those cases where you can't necessarily calculate the reliability of the overall system directly. Instead, what you tend to multiply and to calculate is the probability of the system failing. What's the probability of all of the steps failing at the same time? And I can subtract that from 1 to measure the reliability. So if you look at the equation, you'll see 1 minus R1, 1 minus R2, 1 minus R3, because those are the defect rates associated with that. So if I've got step 1 is 90% reliable, then I know that the odds of failing is 10%. So 1 minus R1 would be 0.1, right on down the line. So I multiply together all of the different defect rates from the reliability. So that's an AND logic. What's the probability that 1 and 2 and 3 and right on down to N that they will all fail at the same time? That's an AND logic. So that's the equation that you see here. And since what I was interested in is the probability that it would not fail, if I know the probability that they'll all fail, I subtract that from 1 to get the reliability of the system overall. So a two-step parallel process where each step, say, is 90% reliable is 1 minus 0.1 times 0.1, which ends up being 99% reliability. So when I'm dealing with OR logic, when I'm dealing with parallel reliability always goes up because I'm basically adding things together. So if I have a two-step parallel process and each of the individual steps is 90% reliable, the overall system is actually 99% reliable because there's only about a 1% chance those two 90% components will fail at the same time. So series calculations is AND logic, and my reliability tends to go down. Parallel is OR logic, and my reliability tends to go up. Often you'll have a system, a more complex system you have to model. And if you understand the equations of probability, you'll have no trouble calculating the reliability of any given arbitrary system, of any given arbitrary complexity, as long as you basically remember one rule. If you've got parallel pieces, you've got to resolve them first before you do the multiplication. So resolve your ORs before you resolve your ANDs. So in this example, in red, the A, B, C, D series, in order to do the full system reliability, you first have to collapse the two C equations into a new reliability value for just that step, which would be C prime in this example. So always collapse your ORs before you combine your ANDs. And based on the structure of your system, you might have to do any number of different comparisons, but the actual calculation of system reliability for any complex system is actually quite simple if you simply remember the rules of basic probability. One more thing to throw in, we talk about series reliability and parallel reliability. There is a third kind of reliability that also obeys these rules, and that's backup reliability. The equation for backup reliability is just a little bit different, because where in parallel, both components run at the same time, we calculate the odds of them failing. The definition of a backup is that we only use the backup if the primary component fails. But again, it's an OR logic, so it's additive. I've got reliability 1 is the reliability of the primary system. Then I can add to that the reliability of the backup system multiplied by the failure rate of the first system, or 1 minus R1. So again, if I've got reliability 1 and reliability B are both 90%, I'm going to get a 99% reliability out of that. It turns out in the calculation that the reliability with a backup gives you the same answer as a parallel system with two components, but the equations are different. As soon as you have more components and more backups, that parallelism doesn't apply. So you want to use the right equations. Going back to our text, to calculate many reliabilities, you have to, or probabilities, you've got to be able to know what S is, you've got to know what N is. And very often, that's the hard part. The calculations of the probability is actually quite simple. But figuring out how many successes there are or how many total opportunities there are requires you to do some extra math. And that's where permutations come in. Permutations allow you to look at how many different ways could something happen as we go through. Permutations are such that you're choosing things from a set of opportunities where the order that they occur matters. Combinations are actually much more common. In combinations, you look at the different combinations you can get without regard to what order they occur in. So if you look at the combination equation, you'll see that it includes the permutations equation. So the permutations are basically n factorial over n minus r factorial. That same equation is embedded in the combinations, but we tend to reduce the number farther by r factorial. So if I've got a set of permutations, all of which are really the same, there's many different ways to order 2, 3, or 4 components. But all those components, regardless of their order, would only constitute one combination. So that R prime that gets introduced in the combinations equation there on the bottom is reducing the number of permutations to the number of combinations, depending on how many different variations of the permutations would actually be the same combination. So using permutations and combinations, we can usually figure out, given our domain in engineering, what our S should be and what our N should be, and then apply those values to the equations for probability. So those are the basic rules for straight probability that we need in order to move forward with basic statistical analysis.